Dear students, last class we discussed about the various system parameters of a transmission model, and using that we derived the expression of voltage and current. It's a partial differential equation, a function of distance and time. This is the voltage equation and this is the current equation, and these two equations are called telegraph equation or just telegraphic. In today's lecture, I am going to focus on converting this the linear partial differential equation to a phasor form. So, phasor form is a complex function. There we can see the frequency components, not the time domain, not in a time domain. Rather, it is in a frequency domain. Let's see that how we can convert these two expressions into a phasor form. See, voltage and current are in a sinusoidal moving in a sinusoidal fashion. We can here see that. And taking voltage as a function of Z, so V of Z, and this can be expressed as V of Z times some sin omega t or cos omega t. Let us take it as in the cos. So cos omega t. So we know that Euler's equation e power j omega t, which states that cos omega t plus j sin omega t. So if you take the real part of e power j omega t, it is equal to cos omega t. Now I am going to multiply this part with this V of Z. So this function can be written as, that is V of, which is a function of Z, and t can be written as real part of V of Z times e power j omega t. Similarly, the current function can be also written in the same fashion as a real part of I of Z e power j omega t. Now, if you look at the telegraph equations, here we can see that it is the partial differential equation. I am going to convert this to in phasor form. So in phasor form, all the time domain will vanish. Instead of time domain, the frequency domain content will come. It is just like how we convert a linear differential equation to a complex function using Laplace transformation. The same method we will apply here, and let's see that how we can transform this equation to that frequency domain. So this can be written down as minus r dash I of Z L dash, this time become omega and I of Z. Similarly, the current equation can be converted to the phasor equation. Plus j omega c dash V of Z. Now I am taking these two equations to the next page. Here we can see that this I of Z term is common here. So this equation number 1 and 2 can be written as r dash plus j omega L dash Similarly, equation number 2 become g dash plus j omega c dash times the common component v of z. Now I am going to differentiate this function with respect to dz. This function I am going to differentiate with respect to dz. So this become and we know the expression of this one that we already obtained here. So this is the expression, this one. So I am going to substitute it there. So if you see here minus term is there, the same minus term will come here. Okay. So this can be written down as now I am going to replace this as gamma. So let this r dash plus j omega l dash times g dash plus j omega c dash is equal to gamma square. So this can be written down as gamma square times v of z, or minus gamma square times v of z is equal to 0. This is the voltage equation of the transmission line. Now let us see that the current wave equation, that is we are going to obtain from this function. This is the phasor form. Now we can take it out v of z outside. So this we can write down as g dash plus j omega c dash times v of z. I am going to differentiate this function with respect to ez. So this can be written down as minus tau square I of z is equal to g dash plus j omega c dash times the partial derivative of that v of z. But we know this expression, so if you refer back we can see that. So this is the function there, so we can put it there. But there is a small changes here. If you look at this function, there is a minus will come here, there is a minus will come here, that's minus will come here. So these two get cancelled, so this become plus. Now there is no minus here, it is plus. Now this function, okay, there is no minus here, it is plus. Similarly, I am going to substitute the expression of this function times that function is this one, r dash plus j omega L dash times I of z. Now there is a minus term will come here, there is a minus term, so these two, okay, plus. Now this is gamma square, that's the assumption we have taken, see, gamma square. Now this we can rearrange as gamma square times I of z, or minus gamma square I of z equal to 0. This is the current equation, current wave equation, transmission line current wave equation, where the constant gamma is the propagation constant. So gamma square is, this one is gamma square, then gamma is the square root of r dash plus j omega L dash. This is a series impedance that is multiplied with the shunt impedance, g dash plus j omega c dash, the square root. This r is called the propagation constant of transmission line. If we rearrange this expression, simplify this expression by multiplying the real term and complex terms, we can bring down this alpha in this form of gamma is in this form of alpha plus j beta. So this we have discussed in our earlier lecture. So where is alpha is the attenuation constant and beta is the phase shift constant. So this is the end of this the derivation of the voltage and current wave equation of a transmission line model. So we the first class we describe what the various components in the transmission line model. From that components we obtained the current and wave equation in time domain using Kirchhoff voltage rule and current law. And finally we brought down the expression in the phasor form and we obtained the simplified the current and the voltage wave equation by using the propagation, the complex propagation constant gamma.